telescope, then in Gothenburg, and since 1990 something, it's a faculty at the University of Insubria, which is situated there on the top lake. You can see this image is being flipped. This is north, there is south. And today we're going to talk about the cosmic ionization.
Thank you very much. Let me first thank Andrea and for his kind invitation here and all the organizers. It's a real pleasure to be in Heidelberg. I've been here a few times before. Last time was some 4 years ago. There was a Texas symposium in December along the river. It was I really enjoyed. And okay, tonight I would like to talk a bit about what I'm doing and what I have done on the cosmic ionizing background. And I will start with a general introduction on the subject, just to put the subject in a context. Okay, no, that's possible. Okay, this is a long text that just I grabbed from basically the introduction of all the papers that I published on the UV background. And okay, most of the introduction are the same. And it simply says why the UV background is important. Okay, it's an important quantity because it determines the thermal and the ionization state of the IgM, which is where most of the baryons are. Okay? It's an important quantity for numerical simulations of galaxy formation and of the large-scale structure, and it's important in interpreting the quasar absorption line data and to derive information about the distribution of metals in the universe. Okay, so this tells us what is the UV background. Then I have another very short slide that says what is the reionization. Okay, most of you, I'm sure that know about the reionization, but just to a quick look at the subject. We know that a given ratio of 1,000, the hydrogen helium recombine, the universe became neutral, but today what we do observe is the most of the universe is highly ionized. So we talk about this phase here, the reionization epoch, moving from neutral to ionized intergalactic medium. We are talking about baryons. So the issue here is to understand what are the sources that produce the ionization of the intergalactic medium.
May I interrupt you for a second?
Sure.
A little bit too loud.
It's something that for hydrogen we believe occurs at the ratio around 6 or larger than 6. Okay, this is a short outline of what I will talk in the next 45 minutes. I will just make a brief introduction to dark images and the reionization of the universe. I will talk a bit about the observations of the ionizing sources. I will also touch on the subject, very important subject of the helium reionization, because usually we talk about hydrogen reionization, but it's the other abundant ion in the intergalactic medium, which is helium-2. So we talk about helium reionization, and then I will try to make a brief introduction on the statistics of quasars, absorption lines along the line of sight of distant bright quasars, and then I will be a bit more technical, talk about the radiative transfer cosmology. I will show you a code that is designed to behind this value.
Okay.
The UV background is an important role in astrophysics. Okay? Here are just an example of where the UV background is playing a role. It sets the temperature, the ionization state of the intergalactic medium. It determines what we map the intergalactic medium through the quasar social lines. Of course, it is the source of organization. It has a role probably in the formation of small galaxies. Okay, the H1 beasts in galaxies. For example, the 21 centimeter light tomography through a mechanism that is called pumping. That has a role. And also has a role in the, for example, if you want to compute the gamma ray opacity, the opacity of the universe for the propagation of gamma ray photons has a role because of photon-photon interaction pair, electron-positron pair production. I just show you here a couple of examples. This is a plot that I grabbed from a paper by Heidelberg 2010. They show the number of galaxies, let's say galaxies with a given mass, assuming different UV background. And you can see that at high mass there is not much different, those are different UV background models, but at low mass there is a lot of difference in the number of galaxies that you expect of a given mass. I'm not implying that this is correct or something, just to show that at low mass you have you can have an important effect due to external ionization from the UV background. That's really heating up the gas of in a small galaxy. This is another paper that completely different. That shows this is the opacity. Well, this is the direction at which the universe becomes optically thick, to gamma rays at a given energy. Okay, gamma rays of 100 GeV, 1 TeV, and this is the direction at which the universe is optically thick. Okay, for those photons, you have to remember that basically 1 TeV photons interact with 1 micron photons and produce electron-positron pairs. So the universe is optically thick to these photons, and those are different results assume different cosmic backgrounds. Okay, this is a paper from Gilmore et al. 2009. Okay, so very quickly we have to start from the combination. We know from the basic cosmology that the ration around 1100. The universe recombined. We know that the recombination of hydrogen is delayed because there are two effects. One is the photon baryon number is a large number. It's about 2 billion, 1.5. And the other is that that reaction occurs out of equilibrium. So you have the temperature of the universe when the Heidelberg was small compared, for example, from the Raman continuum energy. So we have the after combination, we have the dark ages, and now I will just show you all the large scale structure information in one single slide. Okay, for dark matter, things are easy. You just have gravity. We know that from matter CDM that the formation of dark matter halos follows a bottom-up hierarchy. You first form small clumps that tend to combine into larger structures, and so now we are living in the era of superclusters of non-linear. But as soon as you put baryons in the context, baryons behave in a different way. Okay, a direction that is about a bit larger than 100. Baryons are free from the photons, from the photon field, and are free to fall into the dark other halos. And basically, this is very sketchy, so it's just to give an idea. And two different things can happen. If the cooling time of the baryons is much longer than the Hubble time, basically the collapse of the baryon is adiabatic, and the baryon are not very interesting for us. They virialize and behave like dark matter baryons, essentially. But if the cooling time is shorter than the Hubble time, the collapse is isothermal. These are two extreme, of course. So the baryons can really lose energy, fall into the dark matter potential wells, and form self-gravitating baryonic objects that sometimes we call top 3 stars. The first source of sources of UV radiation are the first stars formed when the gas was really made by hydrogen and helium, no matters whatsoever about the cosmic values. Okay, these mark the end of the Dark Ages and depends on some kind of decay, some chemistry of the H2 molecules and other things. The direction of the end of the Dark Ages, which is, again, when we form the first sources of radiation in the universe, apart from, of course, the C and B, it's a relation between 2030. Okay, so now we have the formation of sources, and okay, in a standard non-cosmological picture, when you have a source of ionizing photon, you can work a very simple strong green analysis. You have the formation of, for example, H2 region due to the propagation of ionizing photons from your source. You can work out a very simple equation that basically it's a photon balance equation. The number of ionizing photons must be balanced by the number of recombination, and then it ends up with a volume which is occupied by ionized gas, in this case, for example, hydrogen. Everything happens in a recombination time. Okay? When you do this very simple analysis in the cosmological context, you have to take into account a couple of things, a couple of complications. Okay, the first one that you are working in an expanding universe. So the density of your medium, where the ionizing photons are propagating, the density is decreasing because of the expansion of the universe. Okay, the decrease in the density produces an increase in the recombination time, and so everything is changing in time. And the other thing that you have to consider that it's possible to even in ice and of course in the ice and the interstellar things, but you have to take into account that the universe is not a homogeneous medium, and you have to take into account the clumpiness of the baryons, which is usually parameterized by this term here, it's called the clumping factor, that basically tells how many photons you need to ionize a single atom in recombination time. But this is a very old simulation, one of the first simulation I'm aware about the propagation ionization from the cosmological simulation. It's made by Heidelberg and Madame in 1998, and you can see this is a post-processing thing, of course, and you can see the ionization from the different times, which is propagating much, I would say, faster. Here it's in a more extended way into the voids where the density of the intergalactic is lower, while it has the propagation of ionization from has a hard time to propagate through the filaments because it has to ionize a much larger density. Okay? You can easily work out a simple equation that tells you in a very average way, in a very general way, which is the evolution of the ionizing fraction of the universe. Okay, this is Q is the volume fraction of the universe which is ionized ionized at a given cosmic time t, and it is made by a combination of two terms. One is the source terms. In this quantity here, we put all the ionizing photons that are produced by any kind of source that we may want. Okay? These are photons per second per cubic centimeter. Okay? But photons are also absorbed because they are recombined. Okay? So you have to take into account that you have recombination of photons, which is of course proportional to the ionizing fraction divided by the typical recombination. You can, this is a source term, this is a sine term for the UV photons. You can derive, differentiate this relation and obtain a simple differential equation which in a statistical sense describes the transition from a neutral universe to a fully ionized universe. This is very, very general. Okay? This is a simple equation where you have the variation time of the volume fraction occupied by ionized gas. This is the source term and this is the sine term. Okay? What is relevant here to say is that in a static case, at a given time, your recombination time, you reach a static, an equilibrium between ionization and recombination. Here what you have is that since the universe is expanding, as I said before, that the density is decreasing, and so you have usually the volume, the physical volume of your ionized region is always expanding, as soon as you have photons, of course, to ionize the gas. All right. Okay. So, the realization equation you can solve it very, very easily. If you take time which is longer than the recombination time, you have this very simple. So, there's something wrong here. Okay. You were right. Okay. This is the filling factor of ionized gas, which is simple. The number of photons, ionizing photons divided by the number, density of gas times the Fourier recombination times. You say, okay, I call reionization equal when Q is equal to 1. Okay, when all the universe is fully ionized. You work out this very simple relation. This is approximate, of course, you can solve the equation in a formal way. But the issue here is that it's very, I think it's easy to understand that to ionize the universe, you need one ionizing photon per ion per recombination time. This is what this relation is telling us. Okay, so one photon, ionizing photon per ion per recombination time. This is the minimum requirement. I think I will. Okay. This is again all simulation by Nick 2000. We show different properties of the different quantities in the volume of the universe. This is the neutral gas density, this is the total density, temperature, and this is the radiation barrier. Okay? Now things are much more important than this, but this, I think it's nice to show this because it's one of the first attempts in doing this kind of things in a high simulation. Okay? And you will see that as long as, I mean, as it's in the terms of the expansion factor, not the expansion factor. Okay? And you see that as the universe expands, you have your ionizing region expands in the universe, and the background, this is the background radiation in some units that we will describe later on. And you see that what you have, that the universe becomes more and more ionized, and at a given point, the different ionization sources around the single sources overlaps. Okay? You have a breakthrough of ionizing photons. Basically, all the ions in the universe can see almost all the sources. Okay? They're not confined to single H2 regions because all the H2 regions overlaps, and you have reionization. Okay. And in the end, what you see is just a tiny fraction of neutral hydrogen, this is hydrogen, neutral hydrogen along the filaments of the large-scale structure. In the voids, in these regions here, the universe is almost completely ionized. Okay? The neutral fraction is very, very small. Okay, so observations. The first observation thing that I would like to show you very briefly is related to what we can learn observing very distant quasars. When we do observe a distant quasar, the light from the quasar has to pierce a fully large-scale structure. This is a simulation, of course. This is VLT, and it's a quasar very high redshift. And what you do see is something like that. Okay? You see the line of emission from the quasar, and shortward of the line of emission, you see the so-called line alpha forest. The line alpha forest is formed by all the intervening absorbing material from the source to the telescope. Okay? And those are very important and basic observations because the observations of the absorption lines along the line of sight of distant quasars can really probe the intergalactic medium in a redshift space. Okay? And so you can make a lot of statistics, a lot of work that are very experts in this room, in this kind of job. And here you see what you observe for a close quasar, redshift 0.16. Okay, this is line alpha emission from the quasar, and this is the line alpha forest, due to intervening material from the quasar to the surface. This is a much farther out quasar, redshift 3.6, and you see that the structure of the material between the quasar and the observer is very, very different. A lot more lines, and the lines are also more dense. The material is more neutral at high redshifts. And you can see easily from this kind of analysis. Okay, the interpretation, as I say, is pretty simple. The radiation needs at a given frequency is redshifted, and so becomes resonant, line alpha, at a given redshift that you can easily compute like this. Okay, and it's scattered of the line of sight. Okay, it's line alpha scattering, so the photons are scattered off the line of sight with the standard cross section, and you can work out the so-called Gunn-Peterson optical depth for resonant scattering. Okay, and this gives the plethora of absorption lines along the line of sight. You can, well, people in the last, I would say, 3 decades have made a lot of work on this. Okay, and you can really do statistics. You have a lot of bright, not many, but a lot of bright with high redshift. You can sample single line of sight and make the statistic of your lines. Okay, this is a paper by this Baker et al. 2001. They show you the spectrum of quasars at different redshift. Okay, from 5.8 to 6.3, almost 6.3. And from this kind of analysis, you can compute the average opacity along at a given redshift. Okay, you average along all your line of sights. You compute the so-called effective opacity, which is the opacity average of all your possible direction. And this is the results from the opacity as a function of redshift. And what we see is that at redshift around 6, from an observational point of view, there is a clear increase in the opacity of distant quasars. Okay? So, to play safe, I may say that what we know from observing distant quasars in the universe, the IgM, the hydrogen, in the IgM is highly ionized at redshift. I would be very conservative here, lower than 5.7, I would say so. Let's say lower than 6. Okay, there are another set of observations about the state of the IgM comes from CMB polarization. Okay, from CMB polarization, these are slides that I got from Francesco in Ferrara, the plant meeting. This is the TE spectrum, and this is the optical, the electroscattering optical depth. Okay, electroscattering optical depth tells what is again, the optical depth in constant scattering, which is seen by seen difference from the redshift 1000 to redshift 0. And the value of the optical depth depends on the ionization history of the intergalactic medium, of course. The universe is neutral at optical 0. As soon as the universe has been ionized, the photons has to pass through a gas of free electrons, and then you have an opacity. Now the latest, you can see here that this is another style into this, because I had here the Doppler value that was 0.083, I guess. This is the latest quantum value of 0.079. But within the areas are consistent. This seems to push the opacity a bit at a lower value. But again, this is something that has to be proven and seen. Okay? The important thing that once that you know the optical depth of the universe, electroscattering optical depth of the universe, you don't know the reionization redshift, because you have to imply, to move from the optical depth to a value from the redshift at which the universe became ionized, you have to assume an ionization model for that. I will see that. Okay, no, I will not. Okay, so we have another slide. Okay, so so far I've talked just about the intergalactic medium in terms of hydrogen, neutral hydrogen. There is another important ion in the intergalactic medium, which is helium-2. Okay, of course, observations of the lambda alpha fluorescence for the helium-2 component is very difficult, and the amount of observations are very low. Okay, this is an example of the same along the same line of sight. This is the hydrogen one. This is the helium one with the wavelength shifted to the hydrogen value. So multiplied by factor of 4. Okay, helium-2 is a hydrogen atom, so all the lambdas are divided by factor of 4. Okay. And there are some observations that this gives an idea of the optical depth, again, as a function of redshift. If you remember a couple of slides ago, I showed that the optical depth of hydrogen is increasing at a ratio of 6. For helium, you see that there is an increase at a ratio around 3. Okay? But as I showed you here in the next slide, this is for the paper of the physicist of Heidelberg 2010, observations are really, you can basically draw any line from here. Okay? What do you think is actually is consistent with an increase at ratio around 3? There are other observations, of course, and one very important observation is the temperature of the intergalactic medium. Okay? I'm not going to talk about details in how you can compute the temperature of the intergalactic medium. It's not an easy business. You have to rely on different assumptions, on numerical simulations, and a lot of other things. But again, there are claims that there is an increase in the temperature, the redshift temperatures in units of 10⁵ Kelvin. There is an increase in the temperature of the redshift around 3. Okay? Which could be consistent with the increase of the opacity ratio around 3 that we see. And the idea is that this increase in temperature is due to the energy input in the IgM that is due to the ionization of the helium-2 into helium-3. Okay, so what can we say when we brief about helium-2? Ionization, of course, a ratio of 3. The process is probably very patchy. There are very few line of sights with good observations, and the results are very different from different line of sights. And there are indications, it's a possibility, there are possible indications of delayed and slow ionization period, which could extend well below redshift 3. So it seems that the hydrogen is ionization of the hydrogen is a fast process, while ionization of helium is extent in the direction, okay, in time. And this could be due, and I'll show you later, to the different sources that are producing hydrogen and helium ionizing fluids. Okay.
Hydrogen and that's there. You only have a broken string.
Yeah, I agree. Yeah. Well, I say this. Well, let me say that. Okay, I agree with you. What I can say is that helium cannot be fast. That's fair. Okay. You compute a lot of line of sights, and what you have about is these statistics. This is an important plot, and I'll show you why. This is the number, basically, gives the number of absorbers along the line of sight for a given column density in hydrogen. And there are a lot of observations of this kind. And you see that you go from 10 to the 12 in centimeters to -2 to 20 to the 22. Okay? Those are observations. Physically, it's not always clear what are you looking at when you see an absorption line in a distant part of spectrum. There are indications from simulation and other pieces of information that the number of absorbers increases with redshift, and the H1 column distribution is not a single power. Okay? Sorry about that. Okay? So the issue is in terms when we want to compute what happened, what is going on, is the number of absorbers when the optical is set around unity, which is column density of 10 to the 17. Okay? So around here. And there are a lot of uncertainties here. Shouldn't already this. Okay. The line alpha forest, the so-called line alpha forest, probably, which are the low column density gas, probably it comes from the voids. When the line of sight passes through a voids between the last case structure in the universe. Then you have the so-called, again, still line alpha forest, but at the lower, at the higher column density, and it's basically when the line of sight is passing close to the filaments in the last case structure of the universe. Then you have the so-called lambda system, where you really intersect a filament, then you may intersect a galaxy halos, and you have this so-called super lambda system. And then, if you are very lucky or unlucky, depends on the point of view, you can pass through a galaxy, and you have a double lambda alpha system. Okay? All this, the material in the universe between the observer and the quasar, there are a lot of structures, and according to the density that you are passing through at a given direction, you have a different absorption. And you can make a statistic. Okay, now we talk about a bit the effective optical depth. The effective optical depth, okay, is due to the combination of all the line of sight. I will skip very briefly through the cosmic ionizing background. Now you have all the information. You have the sources, you have the absorption lines, and you simply have to work out and solve the equation of radiative. This is not a hard equation. It's the standard equation of radiative transfer in cosmology, where you have to take into account the spatial continuous and so the direction of photons. You have a formal solution, okay, where you have the sources for radiation here and the opacity of the IGN. And this is the background. This is what we want to compute, the background. Okay? I will skip this stuff. Let me go quickly. Okay, this is an important thing. What you really observe is the opacity in hydrogen. What you don't really observe is the opacity in helium and helium-2. Okay, you have to model that. You can do this using, for example, Singles Lab, and you can work out the ionization of helium. It's not a tough thing. Let me skip to this, okay? And then what you find, a very simple solution in an optical field regime, where you have the ratio between the helium to a hydrogen one cone is simply proportional to the ratio between the background with the ionizing photons at 1 river divided by the ionizing photon at 4 river. This is in terms of Einstein force. Okay, this is a very simple solution. Of course, you can work out everything in a more detailed way, but the important thing to realize that the opacity of the universe is a function of the background, because it's the background that determines the ionization state of the IGN, and the background is a function of the opacity. So you have to iterate between these two things. You do that. Okay, let me skip through this, which is not really important. You can iterate through that, and finally you have your solution of your radiative transfer equation. You have observed quantities. Okay, observed quantities are H1 distribution, all the statistics that I show you about H1 lines, and then you have sources. Sources are like rising forces. What we know that are possible candidates of source ionizing forces are quasars and star-forming galaxies. Both quasars and star-forming galaxies produces a lot of ionizing photons, so you can rely on observations of the luminosity function of quasars and luminosity function of galaxies. You have to assume a given spectral energy distribution. Then you have two different computations. You have the cosmological transfer code and the local transfer code. And with the local transfer code, you can compute the ionization structure of single absorbers, and you put everything to your cosmological radiative transfer equation. You have recombination, effective opacity, everything. And then you produce a UV background model. The UV background model now is the first trial, because as I say, the local absorption of the system depends on the background. So what you do is just to put again the UV background into your local radiative transfer code and iterate until you reach a given level of convergence. And so there is a code that is called CUBA. This stands for Cosmological. It's about background. I invented this name when I was a postdoc in Space Telescope, and my student was probably the US version, so it's scary. But anyway, and this is the non-physics is changing very rapidly. Okay, okay. This is now show some results. Okay, this is, for example, if we use just quasar. This is the optical field approximation, no absorption whatsoever. This is the first step of my iteration. Okay, power. Quasar is a powerful spectrum. I put the power spectrum into my code. This is a ratio of 3. Okay, this is the value of the background CGS units, 90 minus 22 words per second per square centimeter per hertz per radian, whatever. Okay, after one iteration, what you have is something like that. Okay, you have the hydrogen 1 absorption, helium 2 absorption. This is the Lambda series of helium 2. This is the Lambda series hydrogen 1. This is the re-emission line alpha from the hydrogen itself, because hydrogen also recombines and produces line alpha photons. And I put this spectrum against the code, and I have a second iteration, third iteration, and so on until you reach a given convergence. Okay, now I show you okay, this is, for example, the UV background around the helium 2 Lambda limits. This is the Lambda series, ratio 3 and 5. As I say, ratio 5, much more absorption. And you say, oh, this is Lambda beta absorption, and so on. This is Lambda continuum. And you say that ratio 5, the universe is much more opaque compared to ratio 3. Okay? So okay, now this is just for quasars. And you say, does it work? Not at all. This is the background. Okay? You take the background, you can compute average quantities, the background average over the cross-section for polarization, you can do the polarization rate in the background. It's a measure of the background. And those are results, different kind of results from different observations. There are some points also here. And this is what we expect from quasar only. So Quasar only fail, quasars fail to produce enough ionizing photons. Okay? So you have to run other sources. And all these kind, of course, are galaxies. Okay? Star-forming galaxies. You can make a lot of modeling in that. For example, in my case, I used synthetic spectral energy distribution, usually with galaxies have a code by Jean-Charlot, subcritical manifold, metallicity versus redshift in some kind of fashion. I take a star formation rate density from various authors. There are three very important parameters here that play a very crucial role. One, of course, is the slope of the faint kind of luminosity function. If you have a lot of very faint sources that can dominate the UV background of the galaxy, and of course, from observation, you don't really know how many very faint galaxies you have. And then there is also the problem with dust collection. And then you have one very basic parameter, which is the escape fraction. Because from, I wouldn't say basic principles, I would say from your galaxy simulations on galaxy code, what you have is the number of, for example, star-forming regions within your galaxy, but you don't know how many ionizing photons are actually able to escape from the galaxy and go to the IGN. So the escape fraction is, in my case, a free parameter, and I adjust the escape fraction to fit the observational constraint. Okay, so it's unfair. Okay, this is the contribution for galaxy from differences commuting far UV vicinity. Okay, these are faint galaxies are actually two. This is the chapter luminosity function with different slopes. Okay, and this is what happens. This is the commuting, and you see the 1 Rydberg, 13.6 eV, 1 liter for hydrogen, and this is what I had before from quasar. This is the contribution that I need from galaxies to fit observational constraints. Okay, so I would need a very strongly evolving escape fraction as a function of redshift. The escape fraction has to be very low redshift because quasars are enough to reproduce observation, and the escape fraction has to be large at high redshift. Okay, and okay, this is a check the filling factor with this particular model. I ionize this is the filling factor of hydrogen. Ionized hydrogen is 6.7, redshift is helium-2, just below 3. This is the optical depth of constant spectral optical depth, was tuned at the doubling of parameters, doubling of values, and tuned to prime values, that is here. Okay, those are different UV background redshift 1, 3, 4.9, 6.9. The red one is just from quasars, the black one is quasars plus galaxies. Okay, they are very different. The galaxy plus quasar spectrum is much softer, and you can see this in the background. Okay, so I show you here that's zoom at the helium-2 nanometer different redshifts, and I show you here that's the result in terms of the UV background. Okay, I would say that again that I tune the escape fraction to fit this kind of data, to fit the constant spectral capacity and the requirement of having H1 ionization rate between redshift 6 and 7 and helium-2 ionization redshift 3. Okay? So the question, of course, the next question is it sensible? I mean, can we have galaxies with large escape fraction, about 10% SHR redshift? This is one of the open issues, I think. One of the most important issues. In the next plot, okay, again, I can work out also the temperature relation of the IGN. I will skip this, and I show you very briefly the evolution of the background for redshift 0 bending time. Okay, you see this is galaxy, IGN, this is X-rays, this is redshift, a large energy scale here. A redshift of 3, you have helium 3 Reionsation, back in terms of neutralization. And here you will see a ratio of 6 H2 neutralization. Okay? And this is basically all the models back in time. Okay, this is what happened from the and of course the model has consistent features the same. H1 has a 6.7, E2 2.8, electrostatic is good, fixed H1 integration rates. Again, crucial parameters, favorite of the luminosity function, both for quasar and galaxies, and the escape fraction of the universe. Let me say, okay, this is okay. Let me say a couple of issues. Okay, there are indications that this is the data from the Ionising background, H1 polarization rate, between direction 2 and 4. This is the model that I showed before. This is a model by Francesco and another in Haardt that basically give the same result. But there is a point here, this is an observational point by Cosmological a few months ago, that seems to imply that at low ratio, let's say 0, the UV background actually is 5 times larger than what I predicted with my models or other predicted with their models. So it seems to be a shortage of photons at very low ratio. Okay? It's not an easy way to solve this. There are different options. For example, the galaxy escape fraction can be very high in very small galaxies, in dwarf or even ultra-faint galaxies. Okay? Could be anti-correlated with star formation because you need a high escape fraction here, you need a high escape fraction here, but you need a low escape fraction there. Okay? So you can have AGNs, same kind of AGNs, extra heating from lasers, for example, I've seen a few papers, this is cosmic things, or of course, the more exciting answer could be new sources like gamma ray. Another issue is the faint AGNs. Okay, this is this is the emissivity of one river. You see, this is my model. Okay, and this is a couple of these are AGNs that are galaxies. These are a couple of observations that I used in the past. But now there's a recent claim by Jalom et al. That the emissivity due to AGNs can be much larger. A factor of, I would say it's a factor of 4 larger at this ratio. So they claim that AGN can produce a lot of more ionizing photon than what I was assuming, what people assumed in the past. And this is a possibility. Okay, this is a possibility. I know what. What is this? Anyway, because what I made a very simple calculation of it that I just submitted. I'm not sure if you appear, but whatever. And I could go, okay, if these AGNs are real, there could be some X-rays, and I should observe these X-rays at an unresolved X-ray background ratio 0. Okay? We are very tight constrained with the X-ray background ratio 0 because it's almost completely resolved into local ratio lower than 4 sources. Okay? So there is not much room of having a large population of X-ray sources undetected ratio larger than 5%. Okay? And I made a very quick calculation with another guy in Milano, and we showed that the IGNs can account for a fraction of the ionization budget that is lower than 15%. It depends on a lot of assumptions, of course. It depends on a lot of assumptions. If very high ratio IGNs have a lot of UV and no X-rays, you can do whatever you like. But this could be very, this is very strange. Okay? Another issue, of course, is escape fraction. There are simulations that show that the escape fraction, this is a simulation by Ronald and Sonny Larson. They show the escape fraction is a function of the solar, of the mass of the galaxy, low escape fraction at high mass, high escape fraction at low mass. On the other hand, there are other simulations of Reionsation that show the opposite things. So the issue from the theoretical point of view of the escape fraction is a big issue. I think it's a big open issue. And also from observation, the thing that the escape fraction that at ratio around 3 are very small, about 5%. Okay, they are very hard observations, and there is a paper in preparation in which I'm involved, or escape fraction calculation of 1, that we have just upper limits that are lower than 1%. So it seems that from star-forming galaxies, the amount of ionized radiation that can see is very, very small. So there is a shortage of photons ionized for ratio 0, there is a shortage of photons at ratio 3, and whatever. There are a lot of things that can happen. Another issue, of course, is about between the IgM opacity. There are different ways in which you can compute the IgM optical gap. This is a paper by Francesco. They show that different groups do not agree in the opacity of the IgM using different and even the same methods. So I'm not mentioning that, but this is something that can have a relevance in what I'm saying. Okay, I think I'm done. I was just two conclusive slides. I'm producing proofs into this models for the evolving unique survivor, including the soft modulation that I'm serious, iteration from QSO, piecewise parameterization of the IgM, accurate treatment of the absorber, UV emission for star-forming galaxy. The result is obvious. The UVB is made by a combination of quasar and galaxies. No surprise. Quasar dominates a low reaction, apparently, while galaxy dominates a high reaction. In between is a mixture. This is something that, when I started this work some 20 years ago, it was strange to see, okay, quasar are local sources of galaxy are high reaction sources. But I see that this is the case in this case. And the open issues, possibly open issue. Oh, gee. Sorry about that. Okay. There are a lot of uncertainties with all the input parameters. High rational function, experimental distribution, the escape fraction, the calculus of the IgM, I didn't talk about that. This is another important parameters. For EUP, there are indication ionization of ratio 3. Is it real? I don't know. Other possible sources, for example, X-ray binaries produce a lot of helium-2 ionizing photons. I didn't count that. Behind exotic particles. And four. Okay. When the ionization will occur, ratio 6 or larger than 6, probably I move that around 6 and 7. Okay, AGNs can do it. Is it true? What about faint AGNs? I'll show you that the faint AGNs are probably absurd, but I'm not sure that they can really do the job. Star-forming galaxies, escape fractions and open issue. It's so small in observation that we don't really know what are the galaxies that are responsible for the radiation. Possibly both galaxies. Both galaxies can have an escape fraction 100% in principle. Okay, of course not detected in certain high-ratio observations. If there is a large population of both galaxies with the largest escape fraction that can possibly do the job, this is something that I would like very much to see in the future. And okay, I just put here the last point. The last point that the so-called photon underproduction preservation 0, the Cosmological results in which I'm involved, is it real? I'm not sure. We have made some calculation, and now we have an approved observation of the local of these galaxies to try to measure the local Big background directly. Okay? And to compare these direct measurements with the Cosmological measurements and see what happens. So I will stop here. Thank you.
So now time for questions. As usual, we like to start from the students. Please.
You talked about like two possible times having area value collapse or the isothermal collapse, comparing Hubble time and cooling time.
Yeah.
So like what about the sound time, sound crossing time for the modes in the so the sound crossing time for the modes, like isobaric conditions, do they go also there in the collapse?
I'm not sure I understand your
So
point.
you've been talking about like two possible collapses, an isothermal and area
Okay,
value
but there
collapse.
was, yeah, okay, this was just to show you, I mean, just divide things into a very simple argument, but of course things are more complicated than this. I'm not claiming that the bodies are collapsing in an adiabatic mode or in the isothermal mode. There are a lot of details that you can account for.
What, there are further questions from the students? We open the question session to everyone. Okay.
If you believe that your ionization happened at redshift 6 and 7, where are you planning to hide the free electrons from?
Say it again?
If you believe that the ionization happened at redshift 6 or 7, where are the extra free electrons from that you haven't found?
Well, no, it's fine. I mean, with this kind of model, I have ionization relation 6.7, and I can reproduce the value of the constant scattering capacity. Just the integral of the free electron density from ratio 0 up to ratio 6.7, and it works out very well. It's not.
What is W1 10?
Well, because it depends on the ionization history. They tend to assume a sudden ionization, a step function. If you take into account, I compute the opacity using the time dependence of the filling factor. So I have an any redshift, I have the volume fraction occupied by free electrons, and I can compute the self-consistently. And it works out with this kind of model. You ionize. I mean, the filling factor is unity ratio between 6 and 7. It depends on small details. Of course, if you have a step function, the ionization ratio is about 9.5%. But it just depends on the kind of history that you do. But you do not expect to turn suddenly on all the ionizing sources at the same time with the same amount.
You talk a lot about the escape fraction. So you have helium and you have hydrogen. Do you use different values because the ionization energy is different?
Use the same escape fraction for hydrogen and helium.
Oh, I was talking about, for escape fraction, I was just talking about hydrogen ionizing photons. Okay, for helium, the job is basically due all by AGNs. They have a very hard luminous spectrum for Rydberg, and for AGNs we have indication that the escape fraction of ionizing force from AGNs is around 1%. At least in bright quasars. I'm not sure about faint quasars, but most of the job here is due to L-star objects. Okay, they are pretty bright, and the escape fraction, it's I'm not using any absorption in the AGNs case.
More questions?
So, in order for your model to work, you need mass-dependent and redshift-dependent escape fractions. So I can see a physical reason for mass-dependence because of the different covering fraction, etc. But what would be a physical model for a redshift-dependent escape fraction?
Well, probably it's not the right word. Maybe, possibly. Okay. I see, as you said, a mass dependence. Okay, and I can see a physical reason. There are physical reasons for having a high escape fraction in smaller galaxies. Maybe the redshift dependence is just a byproduct of that. At high redshifts, you have smaller galaxies on average because of the large scale structure evolution, and possibly this can be the answer. But yeah, it's true that it's not an easy way to I can understand the mass dependence. The ratio dependence could be something related to mass. The ratio dependence of the mass. This is the point.
But if you have an upper limit at the mass dependent 9 of 1%, at 1%, then it's hard to reconcile your almost sort of unity values that you need for your models to produce enough photons.
No, well, I don't really need an escape fraction of 1%. I would need an escape fraction that is 10, 20%, a ratio around 5 or 6. That's the point. That's the point. I don't really need unity.
But that's the generator, the Fayette slope as well.
Definitely. The Fayette slope, the minimum luminosity of your integration, there are a lot of.
Does the metallicity affect the escape fraction? Does that change?
Yeah, could be, yeah.
It affects the escape fraction of Lionel photons, so there is a dependence there with rate because of the change in
Yeah.
metallicity, so perhaps it's the same for.
Yeah, but usually when you have a lot of 1 alpha, it means that you have a lot of absorption, internal absorption, right, in your galaxy. So that's one of the problems in targeting galaxies with a large UV emission. Because, for example, if you target 1 alpha emitters and you see very low escape fraction of Lyman continuum photons, this is what you expect in a sense. Okay, so it's not easy. But of course, there's a metallicity, and of course, metallicity depends on with redshift. This maybe can answer part of your question.
You skipped over something regarding the temperatures and how that's modeled. I was wondering if you could show that.
This one?
Well, you were talking about how you model the temperature or how you model the heat rate.
Yeah, let me see if I can go here. Okay, maybe the next one. Okay, this is a paper by this. You can see. Okay, this is a paper that is just submitted by Ewald, Hutchman and others, and there are those are observations of the temperature. This is the bump. I'm not sure I totally believe in this kind of bump, and those are different assumptions about the treatment of the heating of the IGN. Okay, this is for. They use my Haardt models with different assumptions about non-equilibrium, and apparently they can fit the data. Okay, those are the things that are included, and they can fit the data if they consider the fact that most of the new photons are used to heat the new ionizing ions. But I'm not completely. I mean, this is a possibility. It's a way. As far as I understand, this is a way of treating the heating of the IGN, but probably it's not the only one. You know? This is not the only thing that we can do. But in this way, they can reproduce at least. This is at the mean density, cosmic mean density. They can reproduce this bond with a non-equilibrium solution, of course, and this extra helium-2 new bubbles of helium-2 are produced. Because if you take a face value, this is what I tend to include. Just simply non-equilibrium equation and obtain these things very easily. But with that, they are.
Other further questions? Seems to be the case. Let's thank our speaker again.